Hello and good evening to you all. My name is Amame, and today we're going to present the result of our Lab 5 data communication. For our Lab 5, we will be introducing our basic equation in cybersecurity. In our industrial automation, physical decision is driven by the sensor data sent directly to our PLC. If our attacker, for example, hacker, intercepted and modify this data, it can compromise our operation safety. But this our simulation demonstrate how to basic encryption and integrity validation protect an automatic cooling loop. For each our position we be given and our parameter find their purpose and their default. For phase 0 is our reset parameter. As a very top script, we can easily modify them later for our exercise. Here, we are common days. Here we define 90 seconds summation runtime to establish fixed random seeds. So our sensor noise remain exactly the same every time we run the trial. We also predefine our secure keys, our cooling threshold, about 31.5% of 5 Celsius, and our attack window where we fake 80 degrees spike will be jetting from 35 to 50 seconds. But as we run, let's simply clear out our workshop and store this variable into memory. We are opening our figure yet. For our phase 1, if you look at our normal communication, this plain sensor temperature is sent directly direct to our PLC. It's fully readable, which means it lacks confidential. But as we look at the phase 2, we introducing for two types. We introduce the basic teaching equation sharing key, as you can see in figure 2. When we use correct key, the signal perfectly restore the zero error. However, using incorrect key introduce permanent offset, resulting in complete data mismatch. This proves the importance of secret key combination. For our phase 3, for plain path for plain path, and our protected path for calculation only variable tag, as we can see, and region invalid sample hold the less trusted temperature for our 0 and normal. As we run, now look, what happens during cyber attack in phase 3? As we simulated, is tapering attack between 35 seconds to 50 seconds, as we refer down here, where attacker inject mercilessly to 80 degree spikes. For example, for this one is when we accepted directive mode. But below one, if we refer to our data detected and rejected one. About how many from 38 to 50 seconds the time, we have many rejection from here. But on a phase 4, we can compare the expected plain path for protect APS decision by using this coding. For plain decision, protect decision, playing wrong decision, and protect wrong decision. As we as each counter by it, when we run it on the plain path, the PSC completely trusts this fake data, causing the premature turn on the cooling aperture and show the red, this one, red line, for 38 to more. However, on our protected path is implemented the validation tag. The moment this data manipulated, the tag check file, the system reject all altered samples and hold the last trusted value. Consequently, the protected PSC decision remains perfectly aligned with our baseline expectation. What is happening? While our class decision based on key and validation tag are excellent for demonstration for each of our phase from 0 to 4 is our core, but our core concept is confidential and integrity. They are inefficient for real industrial plan because the attacker could easily guess or bypassing our simple arithmetic equation. This is truly a safeguard for our infrastructure by coding, but for each of our PR system, for PSC impact, spoofing detection, for equation, and lastly for our normal communication via our equation. For this, our automatic equation is like securing both meaning our origin and for our cryptographic map to lock down our data integrity, and lastly our key management for each of our phase is alongside active network anomaly monitoring. That's all for today. In our conclusion, ensuring our data integrity communication path for each of our path from normal reset parameter and let's see our PSC impact. When we write in our communication path, is vital to maintaining automation safely by preventing catastrophic physical incident for each our component or then workers for each workplace. Thank you for watching, and that's all for today. Oh, Leslie, if we show this, this is when we change our equation key, where we get the result for correct error, then our result for error, then our result. For changing proof, we just modify our sample, protected, and plain path and protected path for PSC decision. For compare our decision is given to plain path for one PSC is coding for 31.5%. Threshold given 0, but the path 0, and if none given is neither. If 13.5% plain path is given 6 or protected path in 10, you be given protected path because here I have higher value. If given 31.5%, if plain path is given to 16 and our protected path is 0, it's an effect on the plain path. That's all for today. Thank you for listening.